So obviously the title is an allusion to the textbook that probably many of you have seen or used. And so I wanted to just start my talk by saying, obviously I did not study with Tate, a bit younger than some of the other speakers, but a lot older than a lot of you. But I did have the opportunity to meet and actually get to know Tate a little bit when I was a postdoc. So I was a postdoc at Harvard for 1 year after grad school, and I went over to MIT for a talk. And I don't remember exactly what the situation was, but it was an evening seminar. Maybe they still have those. And so I bought some lunch or bought some dinner along the way at some food truck. Got to the room half an hour early, and then there was an older gentleman in the back of the room, and I didn't know who it was. So I was like, should I eat here? What do I do? So I apologized to him. I'm like, I'm sorry, I'm early and I was gonna eat here. I hope that's okay. And he looked at me, he's like, of course that's okay. And then he pulled out his own food. So we got to talking, and I had the opportunity to get to know him a little bit over that year. And he was really generous with his ideas and his time, just chatting with me and telling me basically it's okay to not always know what's going on. He was so modest, and that was really helpful to hear as a first-year postdoc. And I had the opportunity to go to his Abel Prize conference in Minnesota that year. And in fact, I remember Dustin and I meeting there because we were the youngest people there and sitting there and just learning about his contributions there. So it is a great honor to be here to talk a little bit about how he's influenced the study of elliptic curves. So as I said, I'll be talking about rational points on elliptic curves, and really his influence is everywhere in the field of elliptic curves, as we've already seen in many of the other talks. So I'm just going to do a quick review. We want to study rational points on curves, and it's a very classical problem, goes back to Diophantus. And we often split the study of curves by genus. And just to point out, today I'm talking about smooth, projective, geometrically connected curves. Everything's very nice. I just don't want to have to keep saying that. So genus zero curves are really well understood, as probably most of you know. We understand rational points completely. They satisfy the Hasse principle, which means that we just have to look for points locally. So if there's a rational point everywhere locally, then there's a rational point over Q, say. Checking for this is a finite computation, so it's very doable. And then once you have the one point, you can find all the other points very easily. The standard picture is you draw a circle and you put a point, and then you just draw rational lines through that point, and then you find all of the other rational points that way. So genus zero is easy. Genus greater than or equal to 2, of course, there was this famous conjecture Mordell, which of course is now a theorem of Falting's, that over a number field, you have finitely many points. I'm not going to say too much about this case, except that, of course, the question is, okay, there are finitely many points, but rational points, but how do you find them? Is there an effective version of Mordell? And there's been quite a bit of work, in the last, I would say, 3 years or so on trying to find effective Mordell. In fact, I just saw a preprint the other day on the archive about effective Mordell, as long as the curve has enough automorphisms. So genus 1 is what we're going to talk about today. So a genus 1 curve can have 0 points, finitely many or infinitely many, so any option is available. And if a genus 1 curve has at least one rational point, then it's called an elliptic curve. Just to set the stage for our terminology, so we have an elliptic curve over a field K. It's given by the solutions to a Weierstrass equation. You've all learned this, maybe in that textbook that I showed on the title page. So you have Weierstrass equation and a marked point at infinity. Over a field not of characteristic 2 or 3, you can make it into short Weierstrass form, because you can complete the square and the cube. And then you have an invariant called the discriminant, which needs to be non-zero. There's also an invariant called naive height, which is, you can define it in several ways. You can have some coefficients on the a cubed and b squared, but more or less that's the size of the coefficients. I want to mention this because we will be using this height in later slides. And then the conductor is another invariant of the elliptic curve, and it's a product of the primes of bad reduction, and in some ways it's a measure of the complexity of the curve. And lots of people like to order elliptic curves, say, by conductor because of that. But it's hard to understand the conductor, and I put in green throughout the talk, things that Tate did. So there's famously Tate's algorithm, which I was reading about in preparation for this talk. So it came out in around 1965, but apparently it was handwritten, and lots of people got copies of these handwritten notes. I mean, somebody here will know much more about this than I do. And then actually appeared in print in 1975, but was very useful for people to compute invariance for elliptic curves. So in summary, basically, you can talk about these elliptic curves, think about things over any characteristic and really over Z or a ring of integers, to talk about minimal models. So over Q, for example, and I'll just go back to the previous slide, when you're talking about y squared equals x cubed plus ax plus b, you could take a and b to not just be in Q, but actually in the integer Z. And you could also choose, by clearing denominators, you can also choose a and b to be minimal in some sense. Just make sure no prime p is such that p to the fourth divides a and p to the fourth divides b, right? You can sort of clear denominators and clear extra powers. So you can ask for that over in general. So this is the sort of thing that Tate's algorithm could give you. I'm putting it a little more simply than it actually is, of course. And then in work with Sayre, Tate also extended this criterion, the Néron-Ogg-Shafrevich criterion, to abelian varieties from Ogg's work for elliptic curves, which basically tells us which primes appear in the conductor. So I had said, the conductor is a product of the bad primes, essentially. And since you heard about Tate modules, I decided to actually write it down. So if you remember from Jacob's talk when he defined Tate modules, so you need to just check when the L-adic Tate modules are unramified, or crystalline in the case that if L is P. Okay. So that was just saying, okay, Tate had a lot to do with just even the very basic things about elliptic curves, which I think everyone knew. And then for rational points on elliptic curves, I think probably most people know that there's this famous theorem of Mordell that says that you have a finitely generated abelian group. So of course, over any field, not just a number field or Q, say even over the complex numbers or over the real numbers, the set of points of elliptic curve is an abelian group, and you have the standard picture of adding points on elliptic curves. But the special thing for rational points is that it's actually a finitely generated abelian group. So you have some torsion part and some rank part. And more generally, of course, you can do this for an abelian variety over any number field, same exact theorem by Wei, that you get a finitely generated abelian group of rational points. So the torsion group is pretty well understood in general, but not 100% understood. So for example, we know which torsion subgroups are possible. Mazur has this theorem, very famous theorem from 1977, that tells you exactly which possible torsion subgroups come up for elliptic curves over Q. And in preparing this talk, actually, I learned that Mazur and Tate had worked before that, and several other people that sort of had ideas that went into the eventual big theorem, but they showed that there's no elliptic curve over Q with a rational point of order 13. Okay, so that kind of idea, obviously I'm simplifying it, but goes into the larger theorem. And then for other number fields, we don't quite know, the exact full story yet, but we know that there's still only a finite number of possible torsion subgroups. So Morel proved that there's a bound on the torsion, essentially, depending only on the degree of the number field. And you get explicit bounds that are exponential in D, and you can write them down. I didn't want to, they're kind of long-looking things. But it's conjectured that these bounds should not be exponential, but actually polynomial in D. They shouldn't be so big. But we don't know in general. And what I wanted to focus on was actually that this is still like a very, very current area of research, if you look at the dates there. So we have lists now of all possible torsion subgroups for small degree number fields. So for degree 2, that was done quite a while ago, but very recently, degree 3, 4, 5, 6, and 7 have come out. So, yeah, you should. Yeah. Right. Okay. That's. Okay. Yeah. So it's. Oh yeah. So Michaela is saying that I simplified it too much. That it's not quite that we have the list of all possible torsion subgroups for that last line. It's only that we know which primes can come up in the torsion subgroups. Yeah. So this is all like, very recent work. And I should also say this talk is not exhaustive. There are so many people here that are doing lots of work related to everything I'm talking about. And I'm sure I'm going to not mention every single thing. And you're welcome to chime in with things. All right. So yeah, so torsion is pretty well understood. We understand at least over Q the options. And over number fields, we're still working on it. And then for computations, we can compute the torsion subgroup over any number field. This is very doable and quite fast. You can tell Sage or Magma to do this. And so I mean, that's going to be in contrast to rank, which is not so computable in general. We also understand the distribution of the torsion subgroup. So for example, over Q, the way I wrote the theorem, this was probably, I would say, known even in the time of Tate, that almost all elliptic curves over Q have trivial torsion. What they really do in this 2017 paper is give precise asymptotics for each torsion subgroup. So for example, if you order elliptic curves, they do it by height. You order elliptic curves by height, this naive height that I mentioned before, which is the size of those coefficients A and B. And then, if you just look at the number of elliptic curves of height up to x, you have approximately x to the 5/6 on the order of x to the 5/6 elliptic curves. And so they show, precisely so, for example, for two torsion, the number of elliptic curves of height up to x that have two torsion, non-trivial two torsion is, or the subgroup is z mod 2 for the torsion subgroup, is about x to the 1/2, for example, instead of 5/6. So it's much smaller in terms of just the asymptotics, and they do that for every possibility. And this, people are working on trying to do this for other fields, for example. And with elliptic curves with various isogenies, and there's been quite a bit of work following this. Okay, so the point is that torsion's pretty well understood. We mostly understand, the possibilities, we can compute it, and we mostly understand the distribution. Okay, and rank is very different. So the algebraic rank of the elliptic curve is that z rank that we talked about before, and we can ask the same sort of questions that we did for torsion. So what ranks are possible, okay? And so, of course, I mean, just by the definition of rank, it is a non-negative integer. And so maybe the better question is, are ranks bounded? For example, can you have a rank 100 elliptic curve over Q? Okay, or rank 1,000? We don't know. It's the short answer, and we'll come back to that. How do we compute the rank of a specific elliptic curve? So again, we could compute torsion, but can we do that for, if I give you some elliptic curve with giant coefficients, can you put that into Sage or Magma and actually get a reasonable output in a reasonable amount of time? And so the short answer is no. If you have very giant coefficients, you cannot do that. With smaller coefficients, we do have methods, and we'll come back to this about how to do that. And then how are ranks distributed? So in the previous slide, we said, okay, for torsion, we understand that most of the time you have no torsion. And that's a good sort of rule of thumb when you're working with elliptic curves, that for your random elliptic curve, you're not going to expect any torsion at all, in some sense. And but for ranks, what do you expect? How many, if you sort of pick out a random elliptic curve, and what does that even mean to pick out a random elliptic curve? We'll talk about that. What rank do you expect? So you can look at three different ways to think about this question, and I'll go through all of these. You can think about some heuristics about how you might expect rank to be distributed. You can look at actual data, so take a bunch of elliptic curves. What does data tell us? And then, of course, we want to have some theorems, so we'll talk about some theorems that have been proved in this direction. And then the last question maybe is not so standard, but how do ranks behave in extension? So if you have an extension of number fields, say, do you expect the rank to stay the same? Do you expect it to grow? What happens there? And maybe a better way to think about this is question 3 is like you fix a number field, K, and you vary your elliptic curves. What happens, right? So maybe go horizontally. How do ranks behave in extensions is a more vertical question where you fix your elliptic curve and you vary your number field. What happens there? Okay, so I mean, these are all kind of basic questions you could ask about the rank of an elliptic curve. All right, so first question was, are ranks bounded? So I got this quote. I took a screenshot of Castles' paper to put it in there, and he says that it's been widely conjectured that there's an upper bound for the rank, depending only on the ground field, but it seems to me implausible because, and it goes on to explain that, you can make abelian varieties with high rank using large coefficients. Okay? So he thought that there shouldn't be an upper bound. Now, this question seems to have lots of people that go back and forth on it, and it's not really clear. And we were talking about this yesterday with some of the experts. It's not clear what the experts think because different experts probably have different opinions, and the mood in the sort of community seems to keep changing. So in Castle's 1966 paper, he thought that ranks would be unbounded. And so some evidence for this, perhaps, was exactly this work around that time by Tate and Shafrevich, and this paper is in Russian, that elliptic curves over the function field fp of t, they found that the ranks are unbounded. Or in other words, they found an example, or multiple examples. But their examples are isotrivial, which means, well, one definition is that the J invariants are in fp, but you can think about it as like, okay, you have an elliptic curve over fp of t, so fp of t is this line over fp, and it means that all of these elliptic curves in this fibration, when you go up to an extension, are isomorphic, essentially. So in that way, it's not a constant family, but it's kind of closer to a constant family than just something completely crazy. But Ulmer did give non-isotrivial examples with arbitrarily large rank later on. So it does seem that for over fp of t, the ranks being unbounded is not just a very special thing about isotrivial elliptic curves. It does happen. So we often use function fields as an analog for number fields, and we often prove things for function fields that we can't prove for number fields. So maybe this gives some evidence that ranks are unbounded for number fields. On the other hand, maybe for the function field C adjoint T, the highest known rank of a non-constant elliptic curve is 68. At least I couldn't find anything in the literature that has a bigger number since then. And over Q of t, I asked Noam yesterday to make sure the record is still 18. And I say at least 18 because it's not provably 18. It's at least 18. And that reference is actually the same as this email here, which is that Noam sent an email in 2006 to the number theory mailing list, the listserv, and found an elliptic curve with rank 28. So, this was the record for many, many years. And so 28, again, it was not exactly 28. It's at least 28. And fairly recently, there was a paper that showed that assuming GRH for this elliptic curve, it would be exactly 28, the rank. But very recently, last year, Noam and Zev, I think Zev's here somewhere, found an elliptic curve with rank at least 29. And again, subject to GRH, it would be exactly 29. So there's another email to the number theory listserv, but that took many years. So from 2006 to 2024, so 18 years to go up one rank. So at this rate, I don't know that we're going to be finding very high rank elliptic curves anytime soon.
2008, the previously best known rank was 24.
Yeah, so actually, when I was preparing for this talk, I was sitting there Googling things like, what should I include? And I found a math overflow question about, ranks of elliptic curves. And I think Joe Silverman actually said that he plotted out, Joe's here somewhere, right? And he plotted out, how the ranks went by year, and it looked kind of linear at that point. So the rank records. So I mean, I don't know what this tells us, except that it's really hard, I think, to find elliptic curves of high rank. I think that maybe that's the take-home point. Because it's really hard to produce points. I mean, you have this equation, right? Y squared equals x cubed plus ax plus b. It's really hard to force solutions, x and y, that are rational numbers in there. That's one way to think about it. It's, not a very complicated equation. It has two variables, or two parameters. And you can see, actually, here, and that's kind of why I wanted to show this, that the coefficients are humongous, right? We only have some limit of computational ability right now, too. Okay, so Of course, so that's the sort of records that we have. There's some recent heuristics. There's a paper of Park, Poonen, Voigt, and Wood, and there's work of Granville and Watkins and a paper of Watkins that suggests that only finitely many elliptic curves actually have rank greater than 21. So of course, these would be these exceptions, or these would be exceptions, the Elkies and Elkies-Klagsbrun curves. But we'll talk a little bit more about heuristics. So it's not, I don't know if that means that more people believe it's bounded again, or but there is some evidence that maybe it's bounded again. Unclear, I think. Okay, so I want to just talk about some tools that we can use to study this. I mean, so maybe I'll just say we don't know the answer to are ranks bounded over Q, okay, or over number fields in general, and I don't think. I'm not willing to put money on it, on either yes or no. I don't know if other people are. Okay, so to study ranks, we have a lot of tools that are more cohomological, and a lot of these come from Tate's work. So, like I said, what is the rank of elliptic curve? We're asking for the rational points, so we're trying to literally find points on an elliptic curve. You could try to enumerate them all, and that is a tool that we do use. Is literally, plug in numbers and try to, find solutions. Okay, but that's, that would be a very bad way to find ranks of elliptic curves. Also, because you wouldn't know if you finish. So we have these other cohomological tools. So there's the Tate-Schaff-Ravage group, which was introduced in other talks, but I want to just review quickly. So the SHA is the kernel of this homomorphism from H1Ka, so this Galois cohomology group, to the product over the local ones. And you can really think about these elements in H1Ka as was said in a previous talk, as principal homogeneous spaces over A. So if we want, we can just talk about the case of elliptic curves to make it a little simpler. You can just think of these elements, this Wei-Chatelet group, as torsors of elliptic curves. And what does that mean? They're genus 1 curves, which Jacobian look like the elliptic curve, essentially. With, and you record the action of the elliptic curve, which is exactly pic naught, or the Jacobian of the genus 1 curve. And so elements of SHA you can kind of think about in a very explicit way, which is that they're principal homogeneous spaces that have local points everywhere, but no global points. So this is exactly the failure of the Hasse principle, which, we knew that the Hasse principle held for genus 0 curves and for lots of other examples, but it does not hold for elliptic curves or abelian varieties in general. And so the famous example, of course, is there are many examples, but historically there is a example with a binary quartic, but then there's this famous example of Selmer, which is 3x cubed plus 4y cubed plus 5z cubed, which is a genus 1 curve that you can think of as a plane cubic in P2, which is points everywhere locally, but does not have a global rational point over Q. And so those are exactly the elements of SHA, if you want to think about it that way. Okay, and then you have Selmer groups, which come up in related work, very closely related to SHA. So A and B here are going to be abelian varieties, and there's going to be an isogeny from A to B that I'm calling phi. And then you can talk about the phi-Selmer group. And usually, there are many ways to define it. I tried to pick an easier definition to write. So you want to think about the homomorphism from H1Ka phi to this product, again, over local cohomology. And the important thing here is that Selmer groups are finite and very computable. Okay? And I'll just try to explain how you think about it in the case where phi is the multiplication by n isogeny. So if you have multiplication by n isogeny, it's called the n-Selmer group, and it satisfies this exact sequence, which on the one hand, you have something about rational points. A of k mod n a of k should tell you something about rational points. And on the other side, you have SHA appearing. Okay, so you want to think about Selmer groups here as something that sort of records the information of the rational points and of SHA. And you can explicitly think about Selmer groups or a Selmer element as, again, like a torsor for a phi or an here. So what does that mean? So for example, for an elliptic curve, let's take the example of an elliptic curve where my isogeny is multiplication by 3. So you're looking for a torsor for E3, the 3 torsion of an elliptic curve. So you can sort of think about as like a genus 1 curve, a principal homogeneous space, whose Jacobian looks like that elliptic curve, and then a degree 3 line bundle on that genus 1 curve. Sort of a rough way to think about it. And so you want to think about things like that, which are in the kernel of this homomorphism. Well, the kernel of the homomorphism is just telling you that the torsor becomes trivial locally everywhere. Torsor becoming trivial locally everywhere just means that it has a rational point locally. Okay? So I'm looking for genus 1 curves in this example, right? Genus 1 curves that have a degree 3 line bundle, but have a local point everywhere. Okay? And genus 1 curve with a degree 3 line bundle is just a plane cubic. So in this case, the 3 Selmer group, more or less, you're thinking about up to, various equivalences, basically plane cubics that have points everywhere locally. Okay? So that's something we can get our hands on, and that's why Selmer groups, in some sense, are computable. That's one reason. There are other reasons that one can compute Selmer groups, and other sort of better ways to compute Selmer groups and think about them that way. But it's something kind of concrete and very geometric, and also you can think about it algebraically. So if you use any computer algebra package, you can compute Selmer groups, usually 2 Selmer, maybe 3 Selmer groups. Sometimes you're lucky and you get up a little bit higher. And you use these to upper bound and compute the ranks and SHA because of this exact sequence that we have here. So you know that the rank, or say if n is a prime, then the p Selmer group for p a prime is elementary abelian p group, so you can talk about its p rank. And so its p rank, the p rank of their p Selmer group, is going to give you a bound for the rank of the elliptic curve that we're talking about, or abelian variety. It's also going to give you a rank for the p, or a bound for the p torsion, the p rank of the p torsion of SHA. Okay, so take-home point of all of this is Selmer groups are great because they're computable, and they let you study the 2 things that you might care about, the rank and SHA. Okay, so they're a great tool. And this is classically called descent. In fact, this is how one computes ranks in general. So many of you may have used Sage or Magma to compute a rank. You type MW rank, Mordell-Weil rank, right, into Sage, and it produces something. But what it's really doing is computing Selmer groups to give you upper bounds, and then trying to find some rational points to give you a lower bound. In other words, it's by day and by night computation that was mentioned before. This is one of those examples where, by day, well, I don't know which one you do at night or which one you do in the day, but let's say by day you compute Selmer groups, so you get the upper bound, and by night you compute points. You do that secretly because that's really ugly, right, and hacky to compute the points, and then you try to meet in the middle. Okay. So this is like literally how we often compute ranks. All right. Here I'm going to just talk quickly because I think a lot of the previous talks have covered this, but there are lots of conjectures about rank. So the analytic rank is the order of vanishing of this L function, and the weak form of BSD says that the algebraic and analytic ranks match. And the strong form is, you've probably seen this many times and seen all these invariants. I won't go through them except to say that you see SHA there, and you see the Tamagawa number and primes divided in conductor, so you see already Tate's influence just in being able to write down the invariants here. Okay, and so earlier talks this morning, for example, explained how BSD is closely related to the Tate conjecture, and that Tate formulated the analogs of BSD for an abelian variety over a global field. And Bjorn also mentioned that the Tate-Shafarevich conjecture is a big conjecture in the field, which is that SHA is finite. And this is just a quote from that 1966 Bourbaki paper. In fact, it's known that if SHA is finite, it's a square for elliptic curves and for some abelian varieties. So the sum abelian varieties is by Tate, and I think from what I could tell from the literature, maybe this was misunderstood and people thought it was true, or some people thought it was true for all abelian varieties, but that's not actually the case. So Mikkel Stoll had an example in 1996, and it's written in this paper by Bjorn and Mikkel in 99 that there are many examples of abelian varieties with non-square SHA, and they actually show, that's a lot, ordering correctly, about 13% of genus 2 curves. And I think all of their examples have Shaw being 2 times a square. And then William Stein later found examples where he could use primes, odd primes, times the square for the size of Shaw for various abelian varieties. So, this is still like not fully understood, of course, what all the options for Shaw are. But I think everyone expects that Shaw is finite. And the finiteness of Shaw, BSD, of course, is stronger, but the finiteness of Shaw for elliptic curves over number field would imply the parity conjecture. That statement is a theorem of the Dr. brothers. The parity conjecture basically says that the parity of the analytic rank and the algebraic rank match. Okay, so you only care about even and oddness. So the parity of the analytic rank is also known as the root number, so, or I guess known as, but it can be plus or minus 1 and for the obvious meaning of parity there. And so we also expect that to be true. There's also things now called the p-parity conjecture, where you ask for the parity of the analytic rank or the parity of the algebraic rank to match the parity of the p-Selmer group rank, p rank. So you can ask for all of these sorts of things to match. And I think, in some cases, the p-parity conjecture is known, and we expect, of course, all of these things to be true. All right. And so, now that we have these tools at our disposal and we know the conjectures in the field, we can ask, what is the rank of a random elliptic curve? So I'm just going to talk about over Q. So we need to specify some ordering to talk about random elliptic curve. Mentioned that before. I'm going to focus on height because that's the invariant that we're able to actually prove anything for. I don't think we have there are a few results, I guess, but not most of the results are ordering by height and not by things like discriminant or conductor. So you can talk about the density of elliptic curves ordered by height with rank I up to height x. So basically you ask, for this proportion, you look at elliptic curves up to height x with rank I divided by the number of elliptic curves with height up to x. Seems obvious, just the proportion up to x. You can take this limit on both sides, and then you can talk about an average. Okay, and of course, this is all only if the limits exist. We don't even necessarily know that limits exist. And this is just an example of something for rank here. You could ask for the same thing you can talk about average anything, in this way. If you have a large number of things, an infinite number of things, you order them and you can, ask for these kind of statistics. All right, and so the philosophy in the field is that elliptic curves should have the minimal number of points. What does that mean? It means it's really, really hard, as I said, to get rational points on elliptic curves. Okay, why should there be extra points that we don't know about? You might get lucky once in a while, but most of the time you shouldn't have random points on your curve. I write down this equation. Why should there be extra solutions to it? So the minimalist conjecture is a product of that, and it says that densities of elliptic curves with rank 0 and 1 are each 1/2. So of course, minimal number of points here, subject to the constraints that we know. So we expect root numbers to be equidistributed, meaning that half elliptic curves should have root number -1, half should have +1, or in other words, parity of the analytic rank should be equidistributed between odd and even. And so in that case, the smallest even number that we can have rank for is 0, and the smallest odd number is 1. So those are the ones where we see all of the elliptic curves, rank 0 and rank 1. So they each have 1/2. Of course, right, this is densities. It doesn't mean we can't have rank 2 curves or rank 29 curves. Okay, this is just, the majority, the vast majority asymptotically, as we defined. Okay, so this conjecture applies to most reasonable orderings. It also applies to other families in many cases, but not all families, of course. So when I say reasonable, I always make this joke, but if you order by rank, this isn't going to work. Okay, so you can't order by anything you want, but ordering by, discriminant or conductor or height, we think it should work. And most other families, meaning, reasonable families. Again, if you force all elliptic curves in your family to have rank at least 1, if you force a rational point on every elliptic curve in your family, then of course you don't expect this distribution. But what you might expect in that case is that they have rank 1 and rank 2. half of the time rank 1, half the time rank 2 if you force a single point on your elliptic curve in your family. So, you can just extend this philosophy to whatever family. Okay, so this originated, I think, or at least it was written down first in Goldfeld's work, and he was talking about analytic rank in quadratic twist families. Okay, so let me just define quickly quadratic twists because we'll be using them. So if you have a short Weierstrass form, I'm just doing it over Q for simplicity here, but you can do it over any number field. You talk about the dth quadratic twist, you can just basically put the d in front of the y squared part. If you want to move it over, you can also write it in the other form, in short Weierstrass form again. Okay, and so there are lots of heuristics, and there's just been a ton of activity on this in the last, well, basically since I was a grad student, I would say, so last 20-ish years, about this minimalist conjecture. And many of these heuristics involve modeling elliptic curves and their variance by random things, so random matrices for the most part, but random things from linear algebra. And in some ways, this is really good because linear algebra is like the one field, well, it's one of the few things in math that we can really, do. So modeling things by linear algebra means we actually can have some hope of understanding them in some sense. And this is part of the Katz-Sarnak philosophy, which is that, various statistics coming out of L functions have to do with random matrices. So I just have a couple of examples here. There are many more. So Delaunay, which was one of the first things I knew about, was he modeled the SHA, or the p-torsion of SHA, by random abelian groups with an alternating pairing for elliptic curves. And I say a la Cohn-Lenstra. So the Cohn-Lenstra heuristics are a set of heuristics that say class groups for number fields behave like random abelian groups, in some finite abelian groups, more or less. And so he's trying to do essentially the same thing, but saying, hey, but we know there's some extra structure in SHA. There's this alternating pairing, the Cassels-Tate pairing. That should have been in green, maybe. So we might as well take all the information we know and then use that to model it. So we have these random abelian groups, and we have this extra pairing that we know about, and then see what that gives us. And then Poonen and Raines in 2012 modeled the Selmer group, the P-Selmer group, by intersections of maximal isotropic subspaces in locally compact quadratic spaces over FP. And I'll say in a moment, I believe, Bjorn can correct me if I'm wrong, but I believe this was motivated by actual theoretical work that we'll get to in a little bit to even think about this question like this. And their model does match the theoretical results that came out. And then extending that in this BKLPR paper, they modeled the full exact sequence here. So not just Selmer, but also SHA and rank, but tensored up. So you look at these ZP modules, or QP modules. Okay, so, and then I mentioned this earlier, this work of Park, Poon, and Voigt and Wood, where they're modeling ranks and SHA by some invariance from a matrix. So they look at random alternating matrices, integer matrices here, and you look at the rank of the kernel, and then you look at the co-kernel, and then it's torsion. Okay, so there are various other heuristics that I didn't mention, and there are also analytic heuristics that give similar results. But the good thing is that I think almost all of the heuristics that we have agree with one another and agree with the minimalist conjecture. So this is a little bit promising. And we also have function field analogs of a lot of these things. This is just a very small number of the kind of work in function fields. But that also gives some evidence that maybe this is the right way to look. All right, and then I said, what about data, right? We have some heuristics that sort of predict what might happen, and then we can ask something about data. And so this was in 2007, there's a bulletin article by these 4 authors, and they give this graph of the average rank versus the conductor, well, log of the conductor, okay? And they were looking at the Stein-Watkins database, which is not exhaustive up to conductor whatever. Here, that it's just whatever's in that database. And this is what the running average rank looked like. Okay, so you take all elliptic curves up to whatever, e to the 14th or something, and then you ask for the average rank up to there. Okay, so it looked like average rank kept going up. And if you look at the left, the axes, right, it's going up and up and up. It looks like it's going up to 0.88, but we said the minimalist conjecture said that, hey, half of curves should have rank 0 and half should have rank 1, which means average rank should be 1/2. This is not looking very promising based on this data. So this motivated us in a paper which we finished in 2016 to look at a larger set of data, and we ordered by height. And again, we were motivated by some theoretical results in the area. And so what we did was actually just exhaustively write down every single elliptic curve of height up to 2.7 times 10 to the 10th. You might ask, why did we stop at 2.7 times 10 to the 10th? It was getting harder and harder to compute further, but mostly it was we got tired, I think. We probably could have gone to 3 times 10 to the 10th if we wanted to. That, pushing it a little bit further would have probably been possible. So it's a little bit arbitrary in that sense. But you can see that the average rank, the running average rank here, does go down eventually. And like I said, this is an exhaustive database because up to height x, you can write down every single elliptic curve up to height x because height just was the size of the coefficients a and b, essentially. Okay, so this is exhaustive, unlike for a conductor. Cremona has a great database of elliptic curves up to conductor, whatever, and that is exhaustive, but it's very hard to write them all down. Whereas for height, it's trivial. Okay, and then so this is the average rank versus the log of the height. So here the axis is the log instead on the right. And the red points here represent samples of curves at that height. So for some reason, actually, I don't know why the axes didn't come up, but that's okay. I thought it did come up in the last time I looked at this. But so we're talking about about 10 to the 15th is where the red points start coming up. Okay, and and because there's no axes, it's hard to show, but let's see. This top line is around 0.885, I think, if I remember correctly, where it starts to turn around. Okay, and then but this bottom here is something like 0.75 or something like that. Okay, so this is well above 1/2 is the point. Sorry about the axes not coming up. And so these red points are just samples, and we couldn't really compute exhaustively at that. It would have taken way too long. But it was possible, for the most part, to actually compute at those heights. So I think it goes up to about height, I want to say this was like 10 to 15, 16, 17, 18, 19, 20 or so. Maybe I'm off by one number. It might be 14 through 19. So up to height about that, it was possible to do it. It just took a really long time for each curve, and so it was very hard. Of course, this was in the early 2010s. I'm sure computers are faster and better now, and algorithms are faster. So you could probably go a lot further. But I imagine that if someone tried to do this now, they would not actually get to the point where you see anything close to 0.5 as the average rank. Okay, it would just go further. And maybe it's worth saying how did we compute these average ranks? So in this database, about 80% of the ranks are unconditional, and then about 20% require you to assume either GRH or BSD or something like that. Because what we do is we use Selmer, to by day compute two Selmer groups and get an upper bound for rank, and then we try to find rational points and go up. And then sometimes, you don't meet, okay? And so maybe you're lucky and you know something about parity from the analytic rank, and then that helps you figure out which one it should be. But sometimes that still doesn't help, right? You get a 0 and a 2 here, and what do you do? Okay, so what happened was, a lot of the times we could actually compute analytic rank decently and show that that was 0, say, in that case. So you could get it down. So analytic rank gave upper bounds. And in other cases, we had to do harder things. We had to compute three Selmer groups, or we had to use the Castle-Tate pairing. So in a few cases, we had to go to 4 Selmer, but not many. The vast majority just sort of worked out well as just by doing the by day, by night computation. Okay, so I imagine this is something you could do further, but my point is only, so we can compute ranks 20% of them had to assume some conjectures, but you can't go much further. And I remember trying to go one dot further at the time. Oops, sorry. Okay. I remember trying to go one dot further here, so I think that was around 10 to 20th, 10 to 21st or so, and everything just always broke. I mean, it just took forever, and then it would return an error. It was just too big. And again, I imagine it's better now. I haven't tried, but there is some limit to our ability to compute ranks. Okay, so this is all the same. When I ask the question, how do you compute ranks? We have ways to do it, but we can't actually do it for big curves. Yeah. So, sorry. So this is average rank, and I think this is about 0.75, and this was about 0.885. Yeah. Sorry that the axes didn't come out. I thought I had included one with axes. I don't know why it didn't show up. And then finally, the last thing I want to say about the slide is the data is available. So the data was on, so Michigan had a subscription to Box, and then they switched to Dropbox, so we had to keep moving all the data around, and we tried to make it publicly available, but I decided this was a mess. Like, I'm not going to be subject to the whims of a university changing their systems. So we asked Drew to put it on the LMFDB, which, if you don't know about, is a great resource for lots of computational things about elliptic curves. You can go into that database, and it has way more information. So you can find all this data on the LMFDB. Just a little advertisement about computations in the LMFDB. All right. So, okay, I think it's time to talk about actually average ranks. So, all right, you have there were lots of results on average ranks using analytic rank, and so bounds got a little better and better. But then in the last 15 years, there's been a big explosion of activity on this. So I think one of the more famous results is this work of Bargava and Shankar that show that the average rank of elliptic curves over Q, ordered by height, is less than this 0.885. And that number is the number I was saying before on the data, which seems to just be a coincidence, but it was kind of interesting. And the way they show this really is that it's really a corollary of this theorem where they prove something about Selmer groups, about average Selmer groups. And this, it's done by using geometry of numbers and sieve techniques to count the Selmer elements. And Selmer elements are what I talked about before, like, plain cubics that are everywhere locally soluble. So it's really getting your hands on Selmer elements and then being able to count them. And these ideas can be extended to lots of other settings, other families of elliptic curves, families of higher genus curves, and abelian varieties. This is a non-exhaustive list of people that work on this kind of stuff. And there are lots of other cool applications about saying, there aren't that many rational points on higher genus curves, for example, by Puna and Stoll. So another big result in the area is even more recent. I put 2017 to 2022 because Alex Smith posted a preprint in 2017, but then has revised the preprint, and there's a new, actually two preprints on the archive in 2022 that are a little bit easier or more general, in fact, and a little bit more organized. And he shows that for the quadratic twist family, so ED, remember, was the d-twist of elliptic curve E. So for a lot of elliptic curves, he has some conditions on what they can be, but for example, trivial 2 torsion makes them allowable here. He shows that the 2 infinity Selmer corank, I'm not defining that, but it's 0 half the time and 1 half the time. And so it's related, of course, to Selmer groups, and it's a limit. And the rank of the elliptic curve is bounded above by the 2 infinity Selmer corank, and it's actually equal if SHA was finite. So more or less, if you knew SHA finiteness, you would know for a quadratic twist family for all of these particular elliptic curves that you have Goldfeld's conjecture. For the algebraic rank, I guess, not the analytic rank, half 0, half 1. So this is a really amazing result. And even without SHA, you get a bound. And I just want to say the key tool here, or one of the key tools, is that when you have a quadratic twist family, the 2 torsion, they all look isomorphic. All the ED2s look isomorphic. So in particular, and not just isomorphic as groups, but actually isomorphic as Galois modules. So the Galois cohomology groups are all isomorphic. And so all the Selmer groups, they live in these Galois cohomology groups. They live in the same ambient space. Okay, so this is a idea that's been exploited by a lot of people, but and it's quite an important idea when you look at quadratic twist families. So if you can try to control these Selmer groups in the same ambient space, and you say, okay, I twist by a little bit, and then what happens in the space? If you change one local condition on your D, and see what happens, you can have some control over the Selmer groups. And so Alex takes this a lot further, and does this in vast generality. And his work also applies to many other situations, to abelian variety families as well as elliptic curves in some cases, class groups, L-power Selmer groups, and many other people have taken up this line of work and gone further. Okay, and then I just want to say some applications of some of these things. For example, from the Bargava-Shankar work, they show that there's lots of elliptic curves with low rank. So at least 4/5 from their original paper, at least 4/5 of all elliptic curves over Q have rank either 0 or 1. This is, of course, ordered by height. And at least 1/5 have rank 0. In fact, it wasn't known until 2010, as far as I can tell, whether there actually exists an elliptic curve with rank 0 over a number field in general. I'm kind of surprised that it was, that was first proved. And I want to come back to this Mazur-Rubin paper in a moment. And in general, over an arbitrary number field, we don't know if there are elliptic curves with rank exactly 1 for all K. And only very, very recently, I think it was early February, this was posted on the archive, David Zwina proved that there are infinitely many elliptic curves of rank exactly 2. Okay? So I just want to say one thing about this, which is this is hard because it's, you can of course produce elliptic curves with, points, and then, you say, okay, I have rank at least 2. Just like we, in Noam and Zev's example, you have rank at least 29. Okay, you found the 29, things that are independent, 29 points that are independent, but then you also have to bound it, right? So it's hard to produce lots of these things where you have some lower bound and upper bound on the rational points, to control it in 2 different directions. So that's kind of why these questions are hard. Okay, and then you have other sorts of applications. So BSD is true a lot of the time. And then this is just a fun sort of application. And the reason I included this is because here, the first set of authors used 2 Selmer, and the second set of authors used 3 Selmer, and they used, so Alex's methods, and here it's using geometry of numbers methods. But both kinds of methods give something about sums of rational cubes. So I thought that was kind of interesting that you can, these 2 ideas are converging in some sense in terms of results. And then the very last thing I want to talk about is that in just the last couple months, there have been 2 preprints by Koeman Zambrano and then Levent, Manjul, me, and Ari that show that Hilbert's 10th problem has a negative answer over the ring of integers of every number field. And so maybe you don't know what Hilbert's 10th problem is, but at first when you think about it, and I'll say in the next slide what it is, it doesn't seem to have to do with elliptic curves, but it really does have to do with elliptic curves and abelian varieties. And so that's what I was saying is maybe surprising to the non-experts at least. All right, so very brief overview of Hilbert's 10th problem. So the question, this was Hilbert's ICM talk, well, in the notes of it, is there an algorithm to decide whether an integer polynomial equation in several variables has an integer solution? So integer here was z at the time. And the answer was no, proved these papers. And you could, of course, ask this question in many different directions. You can generalize it. And so you could ask, okay, what if I use the ring of integers, OK, of a number field K instead of Z? Okay, so this doesn't at first sound like it necessarily has that much to do with elliptic curves. But already here, in this theorem of Mazur-Rubin, you can see it must clearly have something to do with elliptic curves because they're assuming the finiteness of Shaw here. And so they answer it, no, assuming the finiteness of Shaw. Murdy and Peston also have other conditional results. And lots of people, over the years, I think Denef was in the 70s, all the way to 2024 or so, have looked at particular classes of number fields. And in work of Robinson and then work of Denef, you see the appearance of elliptic curves already. But maybe the simplest statement is in Bjorn's paper in 2002, I think it was maybe in Ants proceedings, I think. He says, okay, if you want to answer this question, I just called it H10 for simplicity, you just have to find an elliptic curve over Q, and that has the same rank over the extension k here, and it has to be rank 1. Okay? So I won't go into why that's true, but it's an amazing connection of like this question that at first doesn't necessarily look like elliptic curve related, and then this is a question that I was like, okay, something I can understand, ranks of elliptic curves, right? And we're asking about how ranks change in extension fields. Okay? And then there's this other paper which sort of weakens the assumption and starts talking about, oh, maybe you can use abelian varieties instead a little bit here, not just elliptic curves. I won't say it precisely. And then in multiple steps by Bjorn and Sasha Schwappentalk simultaneously, and then Sasha finally went one more step further. This came out maybe in 2019, at least it was in the air. I heard it at a talk, but it is written up in this preprint here on the archive.